The attention mechanism. Imagine you're reading a sentence and your brain quietly underlines every word that matters to every other word. That's exactly what the attention mechanism does inside a transformer, and it's the single invention that changed everything. In 2017, a team at Google Brain published a paper called "Attention is All You Need." That title was a provocation. Before it, most language models processed words one at a time, like reading a book through a keyhole. Attention blew the door open. Every word in a sentence gets to look at every other word simultaneously, not sequentially, all at once. The mechanism assigns a score between any two words based on how relevant they are to each other. The word bank looks at river nearby and scores it high. It looks at money and scores that high too. Context decides meaning. The cost is computational weight. Every word attending to every other word means the math scales quadratically with sentence length. Short sentences are cheap. Long documents are expensive. That's the trade-off baked into the original design. But here's where it turns. Attention wasn't just a better way to handle language. It turned out to work on images, proteins, music, and code. The mechanism generalized beyond anything its creators initially claimed. Researchers scrambled to understand why. The pressure came from every direction. Competing labs raced to exploit it. Hardware companies redesigned chips around it. Within 5 years, attention had quietly colonized nearly every frontier of machine learning. The embedding layer. Before a transformer can think about a single word, it has to turn that word into a number, not one number. A vector of numbers, sometimes hundreds or thousands of dimensions long. This is the embedding layer, and it's where language becomes geometry. The core claim is almost absurd. Words that mean similar things end up close together in mathematical space. King and queen live near each other. Dog and cat cluster together. The distance between points encodes relationship. This isn't hand-coded by engineers. The model learns these positions by training on billions of sentences. The embedding layer is essentially a lookup table. Each word gets a unique ID. That ID maps to a row in a giant matrix. The row is the word's vector. Every time the word appears, the transformer pulls that same vector off the shelf. The pivot comes when you realize this lookup table is also learned. It changes during training. The geometry rearranges itself. Words drift toward better neighborhoods as the model improves. The cost is memory. A vocabulary of 50,000 words times a vector of 1,000 dimensions equals 50 million numbers just for the lookup table. Before a single sentence is processed, the model is already carrying enormous weight. Enemy pressure arrived in the form of rare words and new words. Words the model had never seen during training had no home in the geometry. Researchers invented subword tokenization to fight this. Words get sliced into smaller chunks. Unbelievable becomes fragments the model already knows. The embedding layer adapted, but the tension between known vocabulary and the open-ended messiness of real language never fully disappeared. Positional encoding. Here's a problem nobody talks about enough. The attention mechanism is brilliant, but it's also blind to order. Feed it the words dog bites man and man bites dog, and it sees the same set of words, same attention scores, same output. That's a catastrophic flaw. Positional encoding is the fix, and the solution is stranger than you'd expect. In the original 2017 paper, the team didn't train the model to learn positions. They injected positions using mathematical functions. Sine and cosine waves at different frequencies. Each position in the sentence gets a unique signature made of these waves. Position 1 gets one pattern. Position 47 gets a completely different pattern. These patterns get added directly to the word embeddings before attention even starts. The model never explicitly learns what position means. It absorbs it through the geometry. The lived mechanics are almost invisible to the model itself. Position information flows silently through every layer. The pivot is that later models abandon this fixed approach entirely. BERT GPT and their descendants learned positional embeddings from scratch during training. They discovered that letting the model figure out position on its own produced better results. The original sine-cosine approach was elegant but rigid. Learned positions were messier but more flexible. Enemy pressure came from very long sequences. Both approaches struggled when documents stretched into thousands of tokens. The positions at the far end of a long document became unreliable. Researchers invented relative positional encodings and rotary embeddings to fight this degradation. The problem of where are we in the sequence turned out to be harder than the original paper made it look. The query, key, and value system. Inside every attention calculation, 3 things happen that most explanations skip entirely. Every word generates three separate vectors: a query, a key, and a value. The query is what the word is looking for. The key is what the word is advertising about itself. The value is what the word actually hands over if it gets selected. Think of it like a library search. Your query is the question you type. The keys are the index cards on every shelf. The values are the books themselves. The attention score is computed by comparing the query of one word against the keys of all other words. High match means high attention. Low match means low attention. The scores get normalized using a function called softmax, which forces them to sum to 1. Then the values get weighted by those scores and summed up. The result is a new representation of the original word, now enriched with context from across the sentence. The cost is that Q, K, and V are each produced by separate learned weight matrices. That's 3 separate sets of parameters per attention head. Multiply by multiple heads per layer, multiply by many layers, and the parameter count explodes. The pivot is multi-head attention. Instead of running this process once, transformers run it in parallel dozens of times with different weight matrices. Each head learns to attend to different types of relationships. One head might track grammatical agreement, another might track coreference. The model never explicitly decides what each head does. It emerges. Enemy pressure came from interpretability researchers who discovered that some heads seem to do almost nothing useful. Pruning experiments showed that many heads could be removed without significant performance loss. The redundancy was costly, but also part of why the system was robust. The feedforward sublayer. After attention finishes its work in each transformer layer, something quieter happens. Every position in the sequence passes through a small feedforward neural network. Same network, same weights, applied independently to every single position. This sublayer is easy to overlook. It doesn't mix information across positions. It doesn't attend to anything. It just transforms each position's representation through 2 linear layers with a non-linearity in between. But here's the shocking part. Research suggests this is where a huge portion of the model's factual knowledge lives, not in the attention heads, in the feed-forward weights. Studies from around 2021 showed that specific neurons in these layers activate for specific facts. One neuron might fire for mentions of Paris, another for discussions of legal proceedings. The feed-forward sublayer is functioning like a compressed database. The cost is size. Feed-forward layers are typically 4 times wider than the attention layers. In a large model, they account for the majority of total parameters. The pivot came from experiments where researchers directly edited feed-forward weights to change specific facts the model believed. Change a few numbers in the right matrix, and the model suddenly thinks the Eiffel Tower is in Rome. The implications were unsettling. Enemy pressure came from alignment researchers who realized that if facts live in feed-forward weights, and those weights can be edited, then models could be quietly manipulated without retraining. The entire field of model editing was born from this discovery. What looked like a simple processing step turned out to be the model's long-term memory, layer normalization. Every few operations inside a transformer, a quiet reset happens. Layer normalization standardizes the numbers flowing through the network. It takes a vector, subtracts its mean, divides by its standard deviation, then scales and shifts using 2 small learned parameters. That's it. Simple arithmetic. But without it, transformers collapse. The real story of layer normalization is about training stability. Deep networks suffer from a problem called internal covariate shift. As gradients flow backward through dozens of layers during training, the signal degrades. Values explode or vanish. The model fails to learn. Layer normalization fights this by keeping activations in a stable range at every step. The original transformer placed layer norm after the attention and feed-forward sublayers. Later research, including work that produced GPT-2 and GPT-3, moved it to before those sublayers. Pre-norm versus post-norm. The difference sounds trivial. It isn't. Pre-norm models trained more stably at large scale. The pivot is that layer normalization also affects what the model learns, not just how fast it trains. By controlling the scale of activations, it shapes which features get emphasized. The 2 learned scaling parameters, gamma and beta, give the model subtle control over information flow. Enemy pressure came from researchers trying to scale models to hundreds of billions of parameters. At extreme scale, even small instabilities compound across layers. Teams at DeepMind and Google discovered that certain layer norm configurations caused training runs to diverge catastrophically after weeks of computation. Millions of dollars of compute lost to a numerical instability. The search for perfectly stable training dynamics became its own subfield. The Encoder Architecture. In the original 2017 transformer, there were two halves. The encoder was the first half, and its job was to read. A sentence goes in. The encoder processes it through multiple stacked layers of attention and feed-forward operations. What comes out is not a translation. It's a rich numerical representation of the input. Every position in the sentence has now been contextualized against every other position, multiple times through multiple layers. The encoder doesn't generate anything, it understands. The design choice that made encoders powerful was bidirectionality. An encoder can look left and right simultaneously. Every word attends to every other word with no restrictions. This made encoders ideal for tasks where you need to deeply understand a full input before responding. In 2018, Google's BERT model used only the encoder stack and became dominant across almost every language understanding benchmark. The cost was that encoders couldn't generate text on their own. They had no mechanism for producing new sequences. The pivot came when researchers realized that for many real-world tasks, generation wasn't needed, classifying sentiment, answering questions from a passage, detecting named entities. All of these needed understanding, not generation. BERT-style encoders owned these tasks. Enemy pressure came from the decoder-only models like GPT, which kept scaling and eventually showed that a model trained purely to predict the next word could also learn to understand, if it was large enough. The encoder's dominance in understanding tasks began to erode. By 2023, decoder-only architectures were matching or beating encoders on benchmarks they were never designed for. The Decoder Architecture. The decoder is where transformers become dangerous. It generates, one token at a time, auto-regressively. The decoder takes what the encoder understood and produces an output sequence step by step. At each step, it can only attend to the tokens it has already generated. Not the future, never the future. This constraint is called causal masking, and it's enforced by setting future attention scores to negative infinity before the softmax. The future becomes mathematically unreachable. The design makes sense for translation. You generate the first word of the translation, then the second, then the third, each one conditioned on everything before it. The decoder also has a special cross-attention layer that lets it look directly at the encoder's output. This is the bridge between understanding and generation. The cost is speed. Because generation is sequential, you can't fully parallelize it the way you can parallelize training. Generating a 100-word response requires 100 sequential forward passes. The pivot is that GPT-style models remove the encoder entirely, no cross-attention. Just a decoder attending to its own growing output. These models trained on raw text prediction discovered that understanding and generation weren't separate skills. They were the same skill at different scales. Enemy pressure came from latency demands. Users wanted fast responses. Researchers invented speculative decoding, where a small, fast model drafts several tokens ahead and the large model verifies them in parallel. The sequential bottleneck of generation was attacked from every angle, but the fundamental causal constraint, no peeking at the future, remained untouched. Tokenization. Before any of the architecture matters, language has to be chopped up. Tokenization is the unglamorous first step, and it carries more hidden power than almost anyone admits. A tokenizer splits raw text into tokens. Tokens are not always words, they might be word fragments, punctuation marks, or single characters. The most widely used method is called byte pair encoding, or BPE, developed originally for data compression and repurposed for language models. BPE starts with individual characters and merges the most frequent pairs repeatedly until it has a fixed vocabulary. Common words become single tokens, rare words get fragmented. The pivot is that tokenization silently shapes what a model finds easy and what it finds hard. Languages with rich morphology, like Finnish or Turkish, get fragmented far more aggressively than English. The model sees more tokens per sentence and has to work harder to extract meaning. English-centric training data means English-centric tokenization efficiency. Non-English speakers get a worse model for the same compute. Numbers are another casualty. The number 9,472 might become 3 or 4 separate tokens. Simple arithmetic becomes a multi-step token reconstruction problem. Enemy pressure came from multilingual researchers who documented these disparities rigorously. Some tokenizers use 3 times as many tokens for the same information in certain languages. Efforts to build language-neutral tokenizers gained urgency. The cost of bad tokenization wasn't just efficiency, it was fairness. A model that fragments your language more aggressively is, in a measurable sense, less capable in your language. Tokenization turned out to be a political choice disguised as an engineering decision. Scaling laws. In 2020, a team at OpenAI published a paper that rewired how the entire field thought about progress. The paper was about scaling laws. The finding was clean and terrifying. Model performance improves predictably as you scale three things: model size, dataset size, and compute. Not randomly, not in fits and starts. Predictably, like a mathematical law. The relationship followed a power law curve. Double the compute and you get a reliable improvement in loss. The implication was immediate. You didn't need architectural breakthroughs to build better models. You needed more. More parameters, more data, more chips. The pivot is what the scaling laws implied about the future. If the curve continued, and the evidence suggested it would, then the organizations with the most compute would build the best models. Period. Not the cleverest researchers, the richest organizations. The cost was concentration. Building frontier models became a capital-intensive race. The barrier to entry climbed toward hundreds of millions of dollars. Enemy pressure came from a follow-up paper in 2022, the Chinchilla paper from DeepMind, which showed that most large models had been trained wrong. They had scaled model size too aggressively relative to data. A smaller model trained on more data outperformed a larger model trained on less. The scaling laws were real, but the community had been reading them incorrectly. Billions of dollars of compute had been spent on suboptimal configurations. The Chinchilla paper forced a recalibration that rippled through every major lab simultaneously: the training process. A transformer doesn't arrive knowing anything. It starts as a random number generator. Every weight in every matrix is initialized to small random values. Then training begins, and it's essentially organized error correction at enormous scale. The model sees a sequence of tokens. It predicts the next token. It checks its prediction against the real answer. It measures how wrong it was using a loss function. Then backpropagation runs. The error signal flows backward through every layer, and every weight gets nudged slightly in the direction that reduces the error. This happens billions of times. The pivot is that this simple prediction task, guess the next word, turns out to teach almost everything: grammar, facts, reasoning patterns, coding syntax, translation. The model never receives explicit instruction on any of these. It absorbs them as a side effect of getting better at prediction. Enemy pressure came from training instability. At scale, gradients could spike unpredictably, corrupting weeks of training. Teams developed gradient clipping, learning rate warm-up schedules, and careful weight initialization strategies to fight this. A single misconfigured hyperparameter could derail a multi-million-dollar training run. The cost was also environmental. Training large models consumed megawatt-hours of electricity. Data centers ran hot. The carbon footprint of a single large training run drew serious scrutiny. The transformation from random noise to coherent intelligence happened invisibly, inside matrix multiplications, over weeks of continuous computation, on thousands of specialized chips running in parallel. Fine-tuning and alignment. A pre-trained transformer is capable, but feral. It will complete any text in any direction, including harmful ones, because it learned from the full chaos of the internet. Fine-tuning is the process of steering it. The most influential method is called reinforcement learning from human feedback, or RLHF, and it was central to the creation of ChatGPT in late 2022. The process has 3 steps. First, human labelers write examples of ideal responses. The model trains on these. Second, human raters compare pairs of model outputs and pick the better one. A separate reward model learns to predict human preferences. Third, the language model is optimized using reinforcement learning to maximize the reward model's score. The pivot is that this process doesn't just make the model more polite. It reshapes what the model believes it should do. The model learns a new objective, layered on top of its original prediction objective. These 2 objectives can conflict. Enemy pressure came from researchers who showed that RLHF-trained models could be manipulated into harmful outputs through carefully crafted prompts. The alignment was real but shallow. It was a behavioral layer, not a deep value change. The cost was a new kind of brittleness: jailbreaks, prompt injections, adversarial inputs that slipped past the reward model's learned preferences. The field of red teaming emerged to stress test these boundaries before deployment. The feral model was never fully tamed. It was managed. What you're looking at across all of these mechanisms is a single unified architecture that turned out to be one of the most general-purpose learning machines ever built. Not because any one piece is magic, but because the pieces reinforce each other in ways nobody fully predicted in 2017. Attention gives context. Embeddings give geometry. Scaling gives capability. Fine-tuning gives direction. The transformer didn't replace intelligence. It reverse-engineered a narrow slice of it and then scaled that slice until the slice became vast. The sting is this: every capability that surprises you was already latent in the training data. The transformer didn't invent knowledge. It learned to retrieve it faster than we expected.